In this video, I'm going to cover the Marvel Schebler MA-3SPA carburetor. This particular carburetor has the accelerator system as well as a manual mixture control, which all Marvel Scheblers do. So let's get started. So with any carburetor system, we can usually divide it up into two different circuits, the idle circuit and the off idle, or sometimes called the main circuit. So what we're going to do is we're going to start with the main circuit on this carburetor and go through all of the steps that fuel and air will take, all the path fuel and air will take to get to the engine. So let's start at the beginning. Looking at the carburetor, fuel is going to come in right here through the inlet right here. Now on the inlet side here, we all notice that there is a screen, a rather beat up screen, but it's a screen nonetheless. And consider the fact that fuel is going to come this way. So any debris that the screen is actually filtering out will be on the inside. It will not be on the outside. Now this screen is something that I would like to take a look at, clean and inspect at least every annual inspection or every 100-hour inspections. I would not let it go much longer than that. Funny story is sometimes I'll ask students, how often would you check that? And they'll say every overhaul. Well, that would be every 2,000 hours, or should be 12 years. But anyway, back to the carburetor. So fuel is going to come through the inlet through this tube right here. And let's take the carburetor apart so we can now take a look at the inside of what is happening. So once it goes through this passageway right here, it is going to come to a needle and seat. And I'm going to pull that apart here so we can take a look at it. Remove the gasket. We'll set that out of the way. Here we have a needle and the seat down in here. So what happens as fuel enters in through the needle and seat, it will fill up the fuel bowl. And when the fuel bowl fills to a very specific point, these floats, now it's upside down of course, will raise up until the needle closes off fuel coming in, and then the fuel will find its height. The height of the fuel is a very specific and important level. The reason why it's specific and important, if we look at the drawing here, you will look at this fuel line right here and notice that this is where the fuel should be, and it comes to a certain point on the discharge nozzle. So looking back at the carburetor, we can see here's the discharge nozzle, and the fuel needs to be at a certain height. If the fuel is too high, then it is too close to the discharge end, and the carburetor will run very rich because more fuel is being drawn out than should be drawn out. If the fuel level is too low, then the carburetor is going to be lean. It's going to run lean because the engine is not going to get as much fuel drawn out of this discharge nozzle that it should be. The venturi, I should say, will not draw as much as it should. And we'll cover that in just a second. All right, so we have a very specific and important fuel level, and we know that the floats will rise up. They will block off the fuel coming in, and as the engine runs, the floats will then drop down a little bit, allowing fuel to come back in and replace what's being used. So, all right, so we have fuel coming in through the needle and seat, filling in the float chamber right here. And when it gets to its height, then as we talked about, the floats are going to close off the needle and seat, and fuel will no longer flow until the engine is running. Now, once it's running, fuel is going to go into this metering sleeve right here. And there's a slot cut right in it over here. Hopefully you can see that. The slot right there, fuel will go into that slot and through a chamber that is drilled in right here to the discharge nozzle. So let's take out the discharge nozzle and take a look at what we have going on here. Here we go. All right, discharge nozzle. We'll take the little lock off and set that aside. So fuel is going to come into this chamber right here. But the very first thing it's going to encounter in this fuel nozzle is this tip right here, the end, which is called the power jet. So the power jet right there, which is the main metering orifice for the fuel going to the engine. So fuel will come through the power jet, as it's called here, and work its way up through the nozzle. Now we have a lot of holes here. We're going to talk about these holes a bit later. This is for the idle circuit. And these holes right here are going to be for the air bleed, which we'll talk about for a second. But otherwise, fuel is going to come up through here and out the discharge nozzle. Now let's talk about what is actually drawing fuel out of the discharge nozzle. Well, looking at the drawing over here, let's talk about the fact that the engine, this is an updraft carburetor, which means air is going to come from the bottom of the carburetor up into the engine, an updraft carburetor. And in this particular carburetor, we have a series of venturis, a primary and a secondary venturi. We'll take a look at them over here on this half of the carburetor. Primary and secondary venturi system set up in there. It's actually one piece, but we name it that way. All right, so the engine up here is running, and as the pistons of the engine draw back on the intake stroke, it is going to draw in a rather large amount of air, and drawing in that air causes air to be drawn up through the carburetor, across the venturi, and into the engine. So the engine is sucking up the air right there. Now, as the air is drawn through the carburetor, it goes past the venturis. And because of Bernoulli's principle, when air is drawn across a venturi, the air must speed up. And whenever the air speeds up, we have a drop in pressure. So again, velocity increases, pressure goes down. So created within these venturis is a vacuum, and that is their job, is to create a vacuum. In fact, these venturis measure the air going through, and the more air that goes through, the more vacuum there will be. And because there's a vacuum, it will vacuum, if you will, the fuel right out of the discharge nozzle. So as less air is drawn across the venturi, then there'll be less vacuum and less air will come out. So if you can think about it, this is, the venturis are sort of the brains of the operation here. They measure the air and pull out the proper amount of fuel from the discharge nozzle to satisfy that quantity of air to operate the engine appropriately. So, all right, so now we know what the venturi does, and we know why the fuel is now being discharged out of that discharge nozzle. We can back up a little bit and say that, and take a look at these holes right here. So these are called air bleed holes. Now, you need to mix air with the fuel that is coming out of the discharge nozzle. And the reason why air is mixed way back in here before the fuel even comes out is to help emulsify the fuel, get it ready to be evaporated, because we want evaporated fuel going into the engine, fuel vapor, if you will. And having these holes right here allows air to get into the discharge nozzle to emulsify that fuel, break it up into much smaller droplets. Smaller droplets are going to have more surface area than one large droplet would. So it not only does that, but it helps the fuel to come out in a nice uniform stream. So where does this air come from? Well, that's probably one of the hardest part about these carburetors, is actually just following the air path sometimes, but it's not terribly difficult when you just take a little bit of time and look at it. So we're going to cover the air passageways of this carburetor. So first thing we have to do is look at, how does air get into the carburetor? Well, we already talked about the air for the engine is going to come across the air cleaner and through the air inlet chamber, right through this big hole throat right here, across the venturis, and then out into the engine. But we have a bunch of little passages inside the carburetor that are doing quite a few things. All right, so number one, we need to vent the bowl right here. It needs to be vented to atmosphere. And number two, we need to get that air that we just talked about for the discharge nozzle. So where does this come from? All right, unlike the MA3 that we talked about in a different video, the air for this particular carburetor does not enter into this area right here. MA3 has a little hole drilled into it. This does not have that. So the only air going this way is going off into the engine. So where this particular carburetor picks up its vent air from is from behind this venturi. Now, possibly you might be able to see that if I hold a light right there. Maybe it will shine through and the camera can see it, but I will just help you out here. There is a hole drilled right here. There is a hole drilled right here, right down in here. And I'm looking for one more hole because I know we got 4. And one more right there. So we have a hole drilled behind the venturi, here, here, and here. Now, anytime you have a hole behind the venturi, what you're picking up, if we look at the drawing over here, behind the venturi is ambient air. So it's not suction air, it's actually closer to the ambient air. If it was suction, then the pressures would be going the wrong way. It'd be sucking air out of the float bowl, and we don't want that. We want air in the float bowl to be equal to what is in the ambient air. So we have these 3 holes drilled in here. This particular hole right here is going to go off to this hole in the accelerating system, which we'll talk about later. This hole right here vents the bowl, and this hole right back here goes into this chamber right here. This is the one we want to talk about right now. Now, normally there's a little tiny screen right over here. I took that out for ease of explanation here. But what this particular passageway does is, maybe we can get a little light down in there. It has one hole going this way, and from this particular chamber right here, there is no other hole going anywhere. Unlike the MA3, which does have many holes going down in there, this one is pretty much blocked off. Little screen, doesn't go anywhere. But air comes down here, goes into this chamber, and comes out of that. That's where the screen comes into play and corresponds to this hole right here. Now, this particular hole right here is drilled in 2 different ways. It has one passageway that goes straight down and one that goes straight back. So it's going to go back to this right here. So the one that goes straight down, remember this is air, is going to go to the discharge nozzle into this area right here. So once again, real quick, the air for the discharge nozzle entered in from behind the venturi, came into this little chamber right here, through this chamber, through a little tiny screen, mesh screen, and then down into this chamber right here, where it's allowed to go either straight down or straight back. And the air that goes straight down goes to these little holes here. They emulsify the fuel for a better discharge and prepare the fuel for being burnt. And that is really all there is to the main discharge system. So let's take a look at one more drawing over here. Here we go. And this is somewhat of a simplified version. So we have the float level, which we talked about is very important, being the proper level so that we don't get the fuel level too high or too low in the discharge nozzle. The fuel goes down through the mixture control valve, and then it goes up into that chamber. And the very next thing it sees is the main metering jet, or in this carburetor, they like to call it the power jet, but main metering jet, power jet, same thing. Then up into the discharge nozzle where air is entered into it. This drawing does not show the air being entered into it. Up and out the discharge nozzle. Go back a slide. Let's see. This one does okay with explaining our air passage. So we have, it's a little different. We have air comes in from behind the venturi, up here actually, and then down through a drilled passageway straight down into our discharge nozzle. All right, so that is the main discharge system. There really isn't much more to it than that. All right, but now we can talk about the idle system. And let's start with why do we have an idle system? Why don't we just have one system? What's going on here? Well, what is going on with this carburetor, anyone like it, is this is idle right here, and this valve is closed. And when this valve is closed, there is only a little bit of air gets in through around this idle valve. It is a very small amount of air that is coming through. In fact, the air amount is so small that it's not enough to activate the venturis. There would be no suction across these venturis because of the little bit amount of air. And that means that nothing would be drawing out, no fuel will be able to be drawn out of the discharge nozzle. So we got to do something different here. We need an idle circuit. So the idle circuit, set this back in here carefully without damaging it, hopefully. All right, the idle circuit, what is doing is it is dependent upon the fact that above here, the pistons are drawing air in, and they are working very hard to draw in as much air as they can. And if you think about this carburetor goes on something like the smallest it would go on would be a Cessna 150 with an 0200, and that would be 200 cubic inches. So you would be drawing for every revolution of the propeller, 100 cubic inches of air needs to be drawn through these little tiny cracks. So you're going to have quite a vacuum built up on top of the carburetor. And because we have this big vacuum built up on the top of the carburetor, we can use that vacuum to draw fuel out. So what I'm going to do is turn this around right here, and hopefully the camera will pick this up. What we have right here in the idle system, there's 1, 2, 3, 4 discharge holes built into the carburetor where it will take advantage of that suction and draw fuel out of these little holes and into the engine. So let's start at the beginning and take a look at what that's going to look like. So again, fuel is going to come in the same way across our screen that we're going to check every annual inspection or 100 hours. And then the fuel is going to go past the needle and seat just like it did before. It's going to fill up the fuel bowl to a level just like it did before, that important and specific fuel level. And then when the engine is operating, the floats will drop down a little bit, allowing fuel to come out of the needle and seat, keeping the bowl at the proper level. The fuel in the bowl will go down through the metering sleeve just like it did before. It's going to go up this channel just like it did before. It is going to go through the power jet just like it did before, but it is going to come to these holes right here that are locked between these two threads. So because there's threads here and threads here, this particular part is isolated from the rest of this. So the air in these holes is not getting to here. So this side is air. This side is fuel. So the fuel is going to go through that power jet and then up from these holes right here in the discharge nozzle. So let's take a look at the drawing over here, and you'll see that the fuel did in fact come through the mixture metering sleeve, through the power jet, through, here's the threads, bottom threads, here's the top threads. So right between the threads, you have some holes drilled right up and into the idle tube. So the idle tube, which is located right there. All right, so let's take this idle jet out and take a look at it so we can see what it looks like. All right, so here's our idle jet right here. And if you take a look at this end, I'm sorry, it's the idle tube, this would be the idle jet. This right here is what limits the fuel at idle going up into the engine. So we have that, and then we have another air bleed hole right there, which is going to do the exact same thing as the air bleed hole in the main discharge nozzle right here. So this one has its holes right there. This one has a hole right there. It's going to do the exact same thing. And since we're talking about it, we can trace that out and figure out where does that air come from? Well, we already did that really. So if we go back to the top right here, we said that there's a hole right back here behind the venturi. The air comes into this chamber right here through a screen down into this hole right here, which is drilled down, if you remember, and back. So it's the hole going backwards that is going to give us the air for this hole right here to help emulsify the fuel. All right, so from that point right here, it is going to go through this hole right here that is drilled almost all the way up to the top right here. So now it gets a little tricky to see in here, but we have 1, 2, 3, 4 discharge holes on this carburetor. So let's talk about why there are 4 and what these 4 holes are doing as the carburetor is operating. So at a very low idle speed, we're not going to need much fuel at all. So because we don't need much fuel, only one of these holes is actually unported. So at this particular idle speed, whatever this would be at the throttle plate in this position, which would be a very low idle, probably around 550, you're only going to get fuel out of this one discharge port right here, which is adjustable, and we will talk about that later. Now, as we add a little bit of throttle, you're going to get a second hole. Because we've now added more air, we're going to need more fuel than this first hole would provide. So the second hole will now start providing some fuel. And as we open a little bit more, the third one will open up providing fuel because we have more air, we need more fuel. So now we're gonna get that. And then eventually we'll have enough air that we need that fourth hole opened up, providing air or fuel out of that fourth hole. So now all 4 of these holes would be providing fuel out to the engine. But what's interesting, when we're back here at this very low idle and we have one hole right there, well, let's talk about what the other holes are doing, because they are now back here on this side of the throttle plate. So let's go to the drawing and take a look at that. So if we look at the drawing right here, you will see that here's the throttle plate in the closed position. It'll be right there. And just like in our carburetor we just looked at, we can see that we have one port open and fuel will be coming out of this one port. Well, meanwhile, with the throttle plate in this position, these two, in our case, 3 holes, are actually going to act as an air bleed, an auxiliary air bleed, because the air pressure in here is going to be less than in here, because this is under a vacuum now. Fuel is being drawn out through there right there. And so it's actually going to pull a little bit of air in through this one, in our case, a third one, acting as additional air bleeds. Then when the throttle opens up a little bit more and uncovers, we'll say, the top 2, then now the bottom 2 are going to act as air bleeds. So whatever's below the throttle plate is going to act as an air bleed because of the way the air pressure is, and whatever's on top is going to be a discharge nozzle. And it's going to work that way until the throttle opens up far enough that all 4 of them, in our case, are uncovered. And at that point, we'll go back to the carburetor here. So at that point, once 1, 2, 3, 4 uncovered, the throttle plate is going to be opened up enough that enough air is going to be coming through the carburetor that by that time, the venturi is quite probably going to be efficient enough that it's going to start drawing at least a little bit of fuel out of the main discharge nozzle. And that is the transition period. So it's transitioning off of the idle circuit onto the main system. And then as the throttle is opened further and further, then the 4 discharge holes right here for the idle circuit will become ineffective because there isn't enough suction here to allow those to operate, and everything will be riding on just the main discharge nozzle at that point. So that would be the idle circuit. So, all right, we're doing pretty good here. We've covered both the main circuit, we've covered the idle circuit, both fuel and air passages. And now we can talk about our mixture system. So the mixture system. This particular carburetor, as well, actually all Marvel Schebler carburetors, works off of a valve. So this is the mixture rod right here that just rotates with this arm right here. So in the cockpit, when we pull it back, we pull back to idle cutoff is what it's called. It's a little bit of a misnomer because it will cut off the fuel no matter what speed the carburetor or engine is operating at, but we call it idle cutoff. It'll cut it off at full power if you so pull it back far enough. And then we push forward in the cockpit, then it would be full rich. So all right, so we have rich and idle. And so what is happening when we do that is this sleeve, this rod right here goes down into this sleeve down in there. And as we looked at earlier, the fuel passage goes through this slot cut in it right over here. And so at full rich position, this sleeve is orientated as into this slot in such a way that there is no restriction whatsoever. It's wide open. But as the carburetor is pulled into lean, this is going to close off a little more, until it gets to a point where really the amount of fuel going through that sleeve is less than the amount of fuel that this is restricting. So this restriction gets smaller than this restriction. Therefore, down here starts to do the metering rather than this jet. So once that happens, now the sleeve is doing the metering, we can start to, in effect, it would be like making this smaller. It's not this, of course, it's this down here. So as that gets smaller and smaller, the carburetor is going to get leaner and leaner until we get to a point where if we pulled it back far enough, it would close this off completely and the carburetor would shut down because no fuel goes through the metering sleeve out to any of the orifices for the engine. So that's why it's called a cutoff. So that is actually a very, very simple system to do. Occasionally, you may run into a problem where a carburetor has been recently worked on, put onto the engine, and run up. And when you pull this into the lean position, the carburetor just continues to run and run and run as though nothing happened. Well, that's because nothing did happen. It's very easy to misalign these, and so that this rod actually ends up somewhere over here instead of into the sleeve. So when you assemble this, you have to be very careful to make sure that actually makes it into the hole, because it is on a flexible shaft. It's easy to miss on that one. So all right, that's the mixture system. Now, this particular carburetor does not have an economizer system. So that makes it real easy. We don't have to talk about an economizer system. If you're interested in the economizer system, take a look at the video on the MA3, because that one does have the economizer, or as some would say, power enrichment system. But this one does have an accelerator system. So when you operate an aircraft engine, it is always a good idea to move the throttle gently and carefully. You should not be jazzing the throttle like it's a car, because our aircraft, we have the big propeller up front that sets up bad vibrations. They don't like it. We have harmonic, I should say dynamic balancers inside of the engines. They don't like it. So everything is done nice and gently and smooth. But there are occasions as a pilot when we get very excited and hit the throttle a little bit too fast. Something runs on the runway. You need to add some power suddenly because you got too low, too slow. And if you open the throttle too fast, there is the risk that because you open this so fast from an idle, it didn't transition and the engine could stumble. Well, that would really get your attention and quite possibly mess up the seats. So that is not a desired effect. So on this particular carburetor, and not all of them have this has an accelerator system. So as the throttle is advanced rapidly, it will give a shot of fuel, an extra shot of fuel through this nozzle right here, this little one hanging out there. So let's take a look at how this works. It's actually quite simple. So we have fuel in the bowl, obviously, because that's the way the carburetor is operating. And over here, we have a plunger assembly. And you can see when I operate the throttle, there's closed. If I operate the throttle, it's going to push this plunger down. And when I close the throttle, it will pull it back up. So we can start with that. So inside of here, there is fuel. There is a hole right there that is going to go through a check ball valve. Underneath this right here, there's some little BBs, if you will, and there's another check ball over here, so a one-way check. So this particular one allows fuel to go this way, and this particular one allows fuel to go that way. So as the plunger is drawn up, this one will close off so that air is not drawn in through here. And that means the only way that anything can get through would be this hole right here. So as the plunger is pulled up, fuel is drawn through this hole across a check valve and fills up the chamber. And that's where we would be in an idle position. And then when the throttle is advanced, then the plunger pushes down. It closes off the check valve on this side, so fuel cannot come back out into the bowl because that would just be pointless. And this check valve opens up, so fuel is allowed to pressurize through here, come through this check ball, around through that casting right there, and up through this discharge nozzle and spray into the engine. Now there's a few other little nuances about this right here. Number one, this chamber right here must be vented. And we looked at this before. There's a hole right back here on this side behind the venturi that is drilled right through here to here. So that's how this part is vented with air. So when the plunger moves up and down, you can have air on the back side instead of having it airlocked and not be able to move well. Next thing you'll notice, there is a spring on here. So I can compress that spring. And what that spring is there for is, imagine, if you will, you had to open the throttle very rapidly and there is fuel in here. So without the spring, the fastest that you could open up the carburetor would be as fast as you can push the fuel out of that little tiny hole. And if this little tiny hole got plugged for some reason, you wouldn't be able to advance the throttle fast at all. So this allows the pilot to advance the throttle rapidly and then the spring to kind of catch up if that's what needs to happen. So that gives you some play in there to open the throttle quickly and then let the plunger go. The plunger is made of leather. They should be lubricated, and this is actually in very good shape. And make sure there's a little bit of lubrication so when it goes into this chamber right here, it doesn't roll and catch. So, all right, we've covered that. There are adjustments over here that allow you to adjust how much fuel you get for the acceleration. You have a small, medium, and large amount of fuel. And what else do we have here? So that covers the acceleration system, I think, quite well. That's really all there is to that. All right, let's move on and talk about adjustments. All right, so adjustments on this carburetor. The Marvel Schebler carburetors are very easy to set up once you understand what it is you're doing and the results that you want and why you get those results. So what I do to set up this particular carburetor, one like this, on any aircraft engine. So let's just assume that it's either a new engine or a new carburetor. We're taking a new carburetor we're putting on. It's going to have some settings done by whoever overhauled it or built it. And usually that is this particular idle adjustment screw, the idle mixture adjustment screw, is turned all the way in and then out 1.5 turns. And that's a good rule of thumb for to start. There's half, there's 1, there's 1.5. So 1.5 times out, that's a good place to start. So we're going to bolt this all up to the engine. We're going to attach the linkage here to the cockpit. And what I like to do is this screw right here is the idle speed adjustment screw. So we only have 2 adjustments on this carburetor: idle speed, idle mix. So it's not terribly difficult to set up from the standpoint of a mechanic. Now, if you're overhauling these, well, then you have to set up some the float bowl, but that's not even hard in itself there. All right, so to set this up, once it's bolted up to the aircraft engine, I like to make sure this idle mixture is out 1.5 turns. And then I like to take the throttle stop. So this is what adjusts your idle speed. And all it does is right there, it provides a stop to dictate how far this plate will open or close. So if I were to screw this in, it opens the plate more. That's all it does. And so we have more air coming through and we're going to get a faster engine. Well, I don't want to have it interfering with what I'm trying to do. So I tend to back it out so that it's really not in play. And then I go into the aircraft and I will start up the engine and warm it up. It's very important that we do all adjustments on a warm engine. And yes, it could potentially idle way too slow. Well, I'll just control that with the throttle in the aircraft. I will open it up until it idles at the speed that I'm very happy with. And I will warm it up. Now, once the engine is completely warmed up, the first thing I want to do is I want to check the idle mixture. All right, so that's the idle mixture. This is what we're going to set first. And so the way that's going to happen is we are going to pull this into lean. So let's take a look at this here. So let me see. That would be rich and that would be lean. So rich. So we'll call this our rich position. We'll call that our lean position. So here we go. We're in rich, full rich. So we're running the engine in full rich and we've warmed it up. And I'm at an idle speed, and I'm going to pull this to idle cutoff. Remember I said it will cut the fuel off at any speed, but we call it idle cutoff. And I'm going to watch and see what happens. I'm going to watch the tachometer and listen. And if it's adjusted correctly, we should get about a 50 RPM rise and then a die. Then you just die suddenly. So what's happening? Why are we getting that 50 RPM rise? Well, let's talk about rich and lean. Now this slide here works well for explaining how a carburetor should run. So a carburetor typically likes to run, you want it to run very rich at idle and also rich at takeoff. All right, why do we want this? So we want it rich at idle because we do not have a choke and a rich mixture will start a little bit easier. Now, I know the FA books and FA test questions all say that the reason why a carburetor runs rich at idle is because there's not adequate cooling at idle. Therefore, the extra fuel provides cooling for an engine. Well, I know that that is just not true. And the reason why is because there are service instructions that from Lycoming and the operating procedures of most mechanics / pilots is that once our aircraft engine has been started and we're idle at warm up, we are going to pull back on the mixture aggressively and get this rich mixture all the way down as low as we can towards a lean position to where it will barely run. And the reason why is because our fuel is heavily leaded, and that lead in the fuel creates problems. It fouls out spark plugs, it creates deposits on the valves, it contaminates the oil. So we want to lean it out as much as we can. And I do that. In my particular aircraft, I aggressively lean when I start up my engine during warm up, and it has never overheated on me. Even on very, very hot days, I will do this and I have no problem whatsoever with cooling. It's just not a function of cooling. All right, but on the takeoff side of things, when we're in a high power setting and at takeoff, yes, we want an aggressively rich mixture here for cooling and detonation protection. Fuel has better detonation characteristics at a rich mixture than a lean mixture. So that's why we want that. But we're over here, we're talking about idle because the only screw we have on here to adjust is idle speed and one for idle mixture. So looking at the chart, we have a rich is up here and lean is down here. And what I want you to do is just kind of imagine this. So any particular carburetor or engine is going to run at its best power somewhere in between a super lean mixture and a super rich mixture, because we can run rich at about 8:1, 8 parts air to 1 part fuel, and as lean as about 18 parts air to 1 part fuel. But it's going to run at best power somewhere around 14:1. All right. So if 14:1 provides the best power. So imagine, if you will, you have an engine and it's we've set the idle. So we're not adjusting the throttle plate at all. If we had a little device and we can make it richer and richer and richer, then the engine would start to slow down because it's just way, way rich. And as we leaned it out, the engine would start running faster and faster and faster until we got to this perfect mixture. And then it would start running slower and slower and slower because now we're too lean. So if we can find the very perfect happy medium between the two, and that word is called stoichiometric for a theoretical, well, it's not theoretical. Stoichiometric is a perfect chemical burn. So it's chemically figured out, but engines are a little bit different because of their air distribution systems. But we will just say that at stoichiometric, if you stick with me on this one, is where we're going to see our RPM the highest. Well, that's called best power, really. That's where your fuel and air mixture are exactly perfect so that the engine gets the best power. And again, if you go rich of that, the engine's going to slow down. If you go lean of that, the engine's going to slow down. So going back to setting up our idle speed, if we were to adjust the idle mixture, if the engine were running and we were adjusting the idle mixture, and by the way, I don't ever recommend adjusting this while the engine is running because you could get hit by the prop and that would definitely ruin the prop and your day. So if we could adjust this while the engine was running, we could actually get it to a point where if we screwed it in, that would be leaning it out because there's a little needle in there that closes off that top passageway. And we screw it in, that's going to lean out the engine. It would start running slower and slower. And then as we started backing it out and richening it, it ran a little bit faster, a little bit faster, a little faster. And now it's going to start running a little bit slower and a little bit slower because we're getting too rich. So the perfect spot for an idle mixture would be turn it back in until it got to its best and the highest RPM, and then back it out so that it slowed down about 50 RPM. Well, because we don't want to adjust this on an operating engine and because we have the idle cutoff, we can do this from the safety of the cockpit. So we set this at 1.5 turns out initially, right? So all the way in very carefully and then out 1.5 turns. We'll just say that's 1.5 right there. I lost count. 1.5, we'll operate the engine, get it warm. We're going to pull this to idle cutoff. And when we go to idle cutoff, we should see the engine rise about 50 RPM and die. So what happened is, as we shut off the fuel here, there was still enough fuel in the passageways to operate the engine for a few seconds. And what happened is it went from being a little overly rich to perfect mixture to super lean to die. It just happened that fast. And so if we get that little 50 RPM rise, that's indicating that we're 50 RPM to the rich side of a perfect mixture, and that's where we want to be. So if we got it, we warmed up the engine, got in there, pulled this back and got 50 RPM, we're perfect, we're done. But we get in there and we pull this back to idle cutoff and we saw 150 RPM rise. Well, what does that indicate? That indicates that we're way too rich. So it was running so rich that as it extinguished the fuel, because we cut it off here, it went from way too rich to perfect. That was 150 RPM rise to a sudden die. All right, so we'd have to close this off a little bit, maybe give it a quarter turn, run the engine, see where it goes from there. Now, what if we pulled back on the mixture and we had no rise whatsoever? Well, that means we were already on the lean side of things. And so we would need to enrich it a little bit, which would be to turn it out a little bit, open the needle into that hole right there, because that needle goes right in that hole. So we back it out a little bit until we got that 50 RPM rise. Now, what happens if I turn it out and I turn it out and I keep doing this and I just don't get any rise whatsoever? It's like something's wrong. Well, something is wrong. And with these particular carburetors, what tends to happen is there's a bushing here and no seal right there where this throttle shaft goes and on this side where the throttle shaft is. And so what happens is they tend to get a lot of play right in here. And so when you have a tremendous vacuum pulling right here, well, it's trying to pull air from wherever it can, and it will pull air and fuel from wherever it can. It will pull it from around the plate right here. It'll pull it out of the discharge nozzles there, and it will pull it from around the bushings right here that are all wore out. And so that is air leaking in across those bushings instead of fuel. And so we have way too much air, not enough fuel. Backing this out doesn't help because the leak is too bad. Or maybe we have a leak right here in the gasket, or a different induction leak somewhere else. But that usually means that there's an induction leak if you cannot get that rise out of there. So anyway, that's setting up the mixture. So remember now, we backed this one out. So we ran the engine, pulled it into idle cutoff until we got that 50 RPM rise. And once we got that, we know this is set perfect. And by the way, this will obviously affect the speed of the engine. We just talked about that. So if I set it at a perfect spot and I'm idling at 500 RPM, but it's really, really lean and it's running at 500 RPM, as I back this out, it's going to enrich in it, and I should see the RPM go up and up and up, remember? And then it'll start to go drop back down once I go too lean. So this will affect the engine RPM. It's not how we set RPM. Make sure you get those two straight. We set the mixture first, and because we could have been way off, that could affect the mixture, the idle speed. But once it's all set and running, and we have the idle mixture correct, then we will operate the engine again, and we will set the controls from the cockpit until we get it to idle at the exact speed we want it. And then we'll lock it in the cockpit. We're going to shut down the engine, and we'll get out. And then all we have to do is say it was locked in right there, is adjust this screw until it just comes up and just barely kisses that arm right there. And then we're locked in. And then we'll give it one more test run, make sure that we open the throttle and close it. Everything it goes right back to the idle speed we wanted to. We're going to do the idle mixture, make sure that worked again. And then we are done and we are set up. So only two adjustments: idle mixture, idle speed. So there we go. All right, let's see. Last thing I want to cover right here is just a few confusing things about a couple of airworthiness directives on this particular carburetor. Now, this is not all of the airworthiness directives. There are many on this carburetor, but there are just a few that tend to trip people up and cause some confusion. And because they're airworthiness directives, we need to take them very, very seriously. So first one I want to talk about is Airworthiness Directive 72-06-05R2. Okay, so the airworthiness directive on the throttle arm causes a lot of confusion. And part of the problem is because the airworthiness directive was written back in 1972 and there have been product improvements since then. And the product improvements haven't really made it into the airworthiness directive, so it confuses people. So let's start off with the fact that the airworthiness directive, first thing that catches people off guard is it does tell you to look at the throttle arm. Look at this picture over here and inspect the clamping screw right here. Now it says in the airworthiness directive to determine whether it has a spot-faced or milled flat for the head of the clamping screw. So there's the clamping screw right there, and you're supposed to determine if it's milled flat or spot-faced. And a lot of people don't understand the difference between those two things. And what's worse is a lot of people guess. When it comes to aviation, please don't ever guess. Find out the right answer. So I'm going to tell you the difference between spot face and milled flat. So when you produce something, a part, we'll look at the carburetor, there are places where screws need to go, right? And that area needs to be flat. And this area right here where this gasket goes and it clamped to the engine needs to be flat. Where this screw goes needs to be flat. So there's places that need to be flat. And so the casting is made and they're kind of rough and then they are flattened out. Well, how they do that is right here. This is milled flat and they take a mill. So a mill is like a cutter that goes on something that looks like a drill press. A mill is a drill press where the table can move around. So they will take a cutter and they will mount this into the table, and then the cutter can actually go back and forth and mill that flat. Now something that is spot faced, and I'll use my little flashlight right here, is where the cutter just came down and touched it and backed off. So it didn't run across something, just came down, touched it and left. All right, so that would be a spot face. This would be milled flat. So what we're looking for, and we can now look at this drawing right here, do you think that was spot faced, this particular drawing, or milled flat? Now, to me, if it was milled flat, they would have cut it all the way across like that. That would have been milled flat. So I would say this drawing is definitely something that is spot faced. Now look at it over here. You can see the cutters are round and it came down and just touched it in one spot. Boom, that right there is this is spot faced. And if it went all the way down here, that would be milled flat. They actually moved the table or moved the part underneath the cutter. So milled flat versus spot faced. And the airworthiness directive does say, determine whether it has a spot faced or milled flat for the head of the clamping screw. Replace any arm having a milled flat with one having a spot faced flat. All right, so you want the spot faced, not the milled flat. Now, given that information, we're going to look at this right here. The first thing you should notice is that drawing looks absolutely nothing like this arm right here. And that should draw some red flags to you right away. And what has happened is this is the newer style throttle arm to prevent what was happening with the other one. With the old system, and if you look at the drawing, you can see how they want you to safety wire it in a very specific way because these two pieces were only held together by this clamping action of the screw. And what could happen is this lever right here would move independent of this stop right here, which is pinned to the shaft. So the part that's pinned to the shaft, it would not be moving with the throttle arm. And that'd be very, very bad if the pilot's asking for more throttle and it's just slipping on the shaft. So the solution was to create this style of arm where there's these little serrations in there and this locking nut right there. So once you engage these serrations and lock that nut down, these two things, they are not going to move at all, especially with that cotter pin being there. So this particular style arm is not part of the airworthiness directive. So if I were looking at a carburetor and I had to deal with 720605 R2, I would write in my logbook that I inspected it and I found that the throttle arm is not the style that is mentioned in the airworthiness directive. So there we go, spot face, milled flat, and the serrated throttle arm. The next one I want to talk about is 93-1904. And that deals with floats. And with the floats, there was a problem. And they said that you are supposed to inspect these floats for the part number CF30766. Now, it just so happens that I grabbed a float with the part number CF30766. And the point I would want to make here is a lot of people make the mistake of seeing that 30-766 and don't realize that the CF is in fact part of that part number, because these floats are made by several different manufacturers. One manufacturer put CF30766, another manufacturer just had 30766. So be very careful and note that the CF is in fact part of the part number. So if these floats only had the 30-766 and the AD said, look out for the ones that say CF, then this one would be in compliance. But again, a lot of the floats don't have the CF, which means it doesn't apply to them. And while we're talking about floats, there have been a progression of floats in Marvel Schebler. There was some black composite floats. There were these metal floats. There were white plastic hollow floats. And now there are blue composite floats. So the problem with the first three, the black composite, the metal floats like this, and the white plastic floats, is that the black ones, I believe, had a problem with disintegration in certain types of fuel. These particular floats, you can see this one is crushed. They're very, very fragile and easily crushed with too much pressure or mishandling. Not only that, they're prone to getting little tiny pin leaks in the solder joints. You can test them out, you can make sure that they work, and then put them in service, and these little tiny pin leaks will leak so slowly that it will eventually fill up and the float will sink. Well, what happens when a float sinks? If a float sinks, that means this needle is not going to be in the seat, and that means that the carburetor will overfill, it will go over rich, and potentially cut off the engine because it's too rich. So very bad thing to have happen. I guess best case scenario is it's going to sink and leak fuel all over the floor, and you'll have a gigantic mess when you come into the hangar the next day. That could lead to a fire. That would be the next worst case scenario, I suppose. All right, so all of those floats, they leaked. And in fact, it's interesting how they will fill up full of fuel, even though they test fine. And that fuel, you can't even find the leak. It won't come out. You can just shake it and hear fuel rattling around in there, and like, well, just wipe it off and it just seems fine, but it's not. Now the blue composite floats, they're not hollow, they're a composite. In fact, they're so well made that even if one broke off, the other one is buoyant enough that it will actually operate properly. So point there being, if you open up a carburetor and it has this style of float, you need to replace it with the blue composite floats. So, all right, and the second point was be careful of part numbers. The prefix on the part number is part of the part number. And the last AD that I want to mention here, just because it's a little confusing for some people, had to do with the Venturi. That was 980106. And what happened is when these carburetors were originally made, these Venturis were in two pieces. There's a primary Venturi and a secondary Venturi, and the secondary is pressed into the housing. And then you would take the smaller one and press that in. And then there would be little clips at all three of these little legs. And what happened is, because it's not really held in with a lot of pressure, this particular Venturi would get loose. And when it got loose and started rattling around, it was subject to falling out and being ingested into the engine, which is a very bad thing. So what the AD wants you to do is either inspect these periodically, I believe it's every 100 hours, or replace them with a two-piece. Well, this AD came out 26 years ago. So for the most part, most of them have been swapped out to a two-piece to a one-piece, because it's labor intensive to take the carburetor apart every 100 hours and verify that the Venturi is not loose in there. But there are some people who preferred the two-piece Venturi, even though it was labor intensive to continue to inspect them. And the reason why is because once we switched over to the two-piece Venturi, a lot of engines didn't run very smooth. In fact, Marvel Schebler had to redesign some of their nozzles. So I think this is one of the very old original ones with an opening here. There's the pepper box style, which has a much smaller hole up top and some holes drilled around the side. So they had to do a bunch of different redesigns to try and get these carburetors to run well once we went to the one-piece Venturi, even though they look exactly like a two-piece. I mean, you can barely tell the difference. The only way that you can tell that this is, in fact, a one-piece Venturi is to take a light and look down in this area right here and see if there's any sort of break between the two pieces. And then just to make sure that it doesn't pop out. So if this was a two-piece, I'd probably be able to grab this inner Venturi and just pop it right out. So that's what that would look like. So there's 3 ADs that I want you to watch out for. Make sure when you're doing these carburetors that you know for a fact that that is not a two-piece Venturi, that you take extra precaution to verify that. And if an engine is running quite well with the setup they have, be careful about changing out the nozzle style, because these two things tend to work well together in this particular circumstance here, and maybe the other style nozzle will not. So there we are. That is the Marvel Schebler MA-3SPA.